Morning, everyone. My name is Bruce Lennox. I'm the Dean of Science, but I'm also a professor in the Department of Chemistry. On behalf of the Faculty of Science, welcome to the 30th edition of Soup and Science. Some of you might have joined us for the summer version, Sun and Science, or maybe you've dropped into the first two editions this week of Soup and Science. But let me just provide some context for what we're doing in this entire series and what we're doing today. So, in other words, other than the catchy title, what's this all about? Why do we do this? So, while every one of your professors, you know them as being a teacher instructor in your courses that you're taking this term, each one of your professors is also a researcher. And this is the nature of McGill being a research-intensive university. So professors do many different things, and outside of the classroom, they spend pretty much all of their time driving research programs forward. So it's our intention, and as you see from the presentations today, that every student in the Faculty of Science at some time during the course of your degree will have a significant research experience. And by that I mean beyond test tube washing. It's about working elbow to elbow with graduate students, postdoctoral fellows, and professors in research programs that cover a vast amount of space in terms of science, but also a great deal of depth. What we really want to impress upon you is that research is not just an enterprise, it's not just an operation, but it's also very, very creative. And I think what you're going to hear today is evidence of that. We don't do research any more than you would say that an artist does painting. Research is very, very creative. And I think what you're going to see today are examples of where the problem selection, there's a great deal of creativity just in the problem selection within a scientific endeavor. Before we begin, let me share with you something that's very important at McGill, and that's our land acknowledgement. We acknowledge that McGill University is on land which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and the Anishinaabe nations. We acknowledge and thank the diverse Indigenous people whose footsteps have marked this territory on which peoples of the world now gather. We have four incredible speakers who'll be presenting their research today. We have Professor C.J. Lee from Chemistry, Professor Courtney Paquette from Department of Math and Stats, Mr. Taj Dyson, he's an undergraduate student in the Department of Physics, and Professor Vicky Kaspi in the Department of Physics. So once the presentations are finished, you'll receive a message from the host to join a breakout room. In this breakout room, will be broken up into smaller groups, and you'll have an opportunity to ask the presenters in your breakout room questions about what you heard today or what research opportunities might lie in their own research programs or that of their colleagues. Each presenter will rotate through the rooms every 10 minutes until they visited each room. But before I introduce our first speaker, it's a great pleasure for me to be able to introduce Principal Fortier to you. She's, of course, principal of McGill, but I'm very proud to say she's also a member of the Department of Chemistry. And I wonder, Principal Fortier, if you could say a few words.
Just a few words, because I know we're all anxious to hear the first speakers this morning. It is an event that I look forward to every year, the Soup and Science series. I've been to it every single year since I've had the pleasure of returning to my alma mater. And the reason is because we get to hear about those very creative, very important questions that people are asking and what they do to try to answer those questions. And it really is inspiring, it's stimulating, and it gives you a sense that no matter where you are in your life, and as you can imagine, my own studies at McGill were quite a long time ago, but you never cease to learn And what you hear at those series is really a feeder to your own curiosity and your own sense of the importance of learning. So I hope you'll enjoy it very much, and I hope that you'll take advantage. There are 2 more days of Soup and Science, I hear. So you should join every day, because every day brings new areas of research and new, very interesting questions. Alors, merci beaucoup d'être ici ce matin. J'espère que vous allez pouvoir vous joindre à cet événement à tous les jours, et je pense qu'on peut même les regarder en ligne après que l'événement ait été fait. Alors, profitez-en.
Thank you, Madam Principal. It's great to have you join us today, and we hope you'll be able to even drop in tomorrow and on Friday. So let's begin with our first presenter, Professor C.J. Lee in the Department of Chemistry. Over to you, CJ.
Right. Thanks, Bruce. First of all, I want to thank the Lennox for inviting me to participate in today's Soup and Science. The chemistry. Sorry. Recently, I think let me back up a little bit. Can I? Okay. Oh, there's a delay. Okay. So recently the U.S. National Academy of Sciences named chemistry as a central science. Because it is the center of all the other science and technology, and also it is related to everything in our modern society, whether the fertilizer for the food, pharmaceuticals, the like cell phones, computers, automobiles, dyes and pigment, and all the fabrics and the clothes that we are wearing, etc. However, the current chemistry and chemical production we know is not sustainable. For example, with ammonia synthesis, it is essential for the world food. However, it consumes roughly about 2% of the entire world energy alone. And also for the fossil energy, and it's completely non-renewable and it's depleting very quickly, plus produce carbon dioxide, which causes like a global climate change. And then all the carbon resource we're using today is based on petroleum. Again, it's non-renewable. And another example is medicine. It's very slow to develop medicine, for example, with the current pandemic, and also highly wasteful. And because it's known over at least 100 kilogram waste will be produced per kilogram of medicine, and these are highly toxic waste. And then there are many other examples. So the green chemistry, the field of green chemistry started not too long ago, is really trying to create some sustainable tools, trying to address these major issues in our modern society. My group is focusing on the developing or inventing new reactions where we can take directly the available natural resource such as hydrocarbons, natural gas, carbon dioxide, water, nitrogen, biomass, etc., and use the simple catalytic process to convert them into highly useful products. And furthermore, we can find ways to directly modify biomolecules quickly, and for example, for medicine. And today I'll just use a couple examples to illustrate some of the chemistry we're doing at McGill. And first one is the ammonium synthesis, as I mentioned earlier. And this is the, so far, all the essentially industrial nitrogen-based chemicals in our society is based on this process called the Haber-Bosch process, given 2 Nobel Prizes in 1918 and 1931. And it's essential for all life forms, and it's a fertilizer for the world supply. It globally produces about 220 million tons of ammonia and contribute about 3 billion people increase in population in the past century. And however, as I mentioned before, consume a lot of world energy, plus it's highly in high pressure, high temperature, and it's difficult to produce. nature uses enzyme to produce them at atoms of pressure and room temperature, and it will be ideal potential green solution if we can do it in the same way. And recently at McGill, we invented a method we can take nitrogen and hydrogen gas at room temperature with the light, produce ammonia. And even better, we can take nitrogen and water, directly use the sunlight, so it's the solar energy, and then produce ammonia and oxygen, which is exactly what nature does. And in fact, this catalyst so far has the highest the record activity being reported so far. Another example is the methane and natural gas conversion. So it's considered one of the holy grails in chemistry, and for a couple of reasons. One is the methane natural gas, the natural abundance is much higher than petroleum, even though it's still a fossil resource. However, it's, first of all, it's more abundant. Secondly, it's much cleaner than petroleum in the short term. And thirdly, methane itself is a large portion of it is actually renewable, and you can generate. And finally, methane, if it escapes into the atmosphere, in fact, it causes global warming. It has a higher greenhouse effect than even. So ideally, you can convert methane and capture methane and convert into a high-value product directly. However, it is very difficult and very challenging. That's why I call it one of the holy grails in the chemistry. And recently, we've in collaborating with me in engineering, we discovered use a simple nanocatalyst. We can convert the methane directly into benzene and other liquid hydrocarbons, and plus hydrogen gas, which can be used for energy supply. And another example is renewable feedstock. I mentioned before, currently the most feedstock for the carbon feedstock for modern society is petroleum. However, it is depleting. And one of the useful or highly useful chemical is aniline, aromatic amine. And it is related to all the dyes, the colors, the fabric, electronic materials, and etc. However, to synthesize aniline, it's extremely wasteful. Actually, one of the most wasteful processes in chemistry, and plus it's very dangerous. And they use the concentrated sulfur gas as solvent with nitric acid to do a nitration, and then do a reduction, and finally alkylation, etc. So the first step actually is the most dangerous and wasteful. And in fact, last year there's a huge explosion in China, destroyed the entire city block by this particular process. However, in nature, there's a lot of aromatic renewable feedstock, which is the lignin. And about 25% of the world biomass is really this lignin material. And there are a lot of research being done and trying to generate some useful product. Recently, people have been able to make all kinds of phenols. And we found actually the phenol be a really good future of aromatic feedstock. And we found you can directly convert the phenol and with aniline to generate aniline derivatives. And again, this is a McGill invention. The last example I want to talk about is medicine. It's the late stage functionalization. So drug resistance has become one of the most critical health issues of the future. And because the microbials, such as bacteria and viruses, they mutate very quickly. However, it takes about 10 years to develop one drug. This is on average. So it's a battle like a human cannot win by the current chemistry. So one possible, at least the solution, even though it's not the final solution, is we can develop some chemistry. We can quickly and modify the structure, modify the medicine in the last step. And however, we don't have a lot of tools available to do this. Recently, we invented a method. We can directly, for example, functionalize the aromatic molecules or including pharmaceutical molecules, ambient condition in water or any other solvent with metal-free, redox-free, and completely bioorthogonal. And for example, if you take the aromatic molecules with this particular design structure, simply by shine light, you produce a product with virtually almost no waste. And you can literally take, for the nucleotide, let's say the DNA or even caffeine or molecule or other biological molecule, and directly functionalize and to generate this product without touching any other functional groups. And this work also has been licensed to Sigma Aldrich for people to use. So this is one example of the trifluoromethyl group, but we have many other related reagents being developed. So in short, finally, there's a great opportunity to use green chemistry to address some of the major issues, modern society. And I want to, of course, thank all the people who work on from my group, who work on the project, different project, and the people who support our research. Thank you.
Thank you, CJ. Thank you. Fantastic work. Truly pioneering work in every one of those projects that you described.
Thanks.
So we'll move over to our next presenter. That's Professor Courtney Paquette in the Department of Mathematics and Statistics. Courtney.
Hi, thank you for inviting me here today. I'm actually a new professor. I just started about a month ago, so I'm very excited to be here and in Montreal, so it's been great. So my research is in optimization, especially with large scale. So as many of you guys might know, optimization is one of these sort of core centers for machine learning and artificial intelligence. It's one of these big ideas. And so today I'm going to talk to you about a project that I'm very much excited about, and I'm hoping maybe some students might be interested also in it. And it's sort of this idea that why large-scale optimization is kind of all the same, that when we do these large-scale data sets, that the optimization aspect actually gets a little bit easier. And so with optimization, it's all about complexity. So this is the idea of complexity of an algorithm. So this is the idea of sort of how much computation it takes for an algorithm to run. How we compare algorithms across each other. So in optimization, we generally measure complexity via something called a worst case analysis, which is that we sort of look at, a bound on the worst input that you could possibly have into your algorithm. And so what this does is it gives you that your algorithm is going to converge, which is great. And it also tells you sort of the maximum number of computations that you need in order for the algorithm to run and actually converge. However, if you think about this from a perspective of like you just ran the algorithm itself, it often doesn't match up to what your actual runtime is as a typical user. So an example of this is this classic simplex method, which was done for linear programming. And it's a famous method. And its worst case complexity is actually exponential. So it takes a really long time. If you look, there's an example of some data set going into it that would take a really long time to actually converge. However, if you and I were just to run it on a typical, we just inputted it just for fun right now, you wouldn't see this exponential. You would actually see it being polynomial. So it behaves much faster, and that's actually why people tend to use it. And so to sort of give a sense of how do we measure sort of a typical user's computational complexity of an algorithm, we sometimes look at something called average case. And so this is the idea that we measure complexity averaged over all the possible inputs that we can put into an algorithm. So it's more representative of, say, a typical user. Now, for example of this, sometimes you can use this average case complexity to actually generate better algorithms. So the classic example of this, I'm hoping some of you have seen this, is in your computer science courses, you saw quicksort. Quicksort in general is terrible, right? If you input into a sorting algorithm, it takes a really long time. But on average, it's actually pretty good. And it was designed so that the average case complexity of this algorithm was pretty fast. However, this idea of average case complexity is just not used in optimization. And one of the issues is that we don't know how to formulate a problem of saying that what is a typical problem in optimization? So what is a typical data set? So we started looking at this, and one way we can say what is a typical optimization problem is we decided to focus on a very classic least squares problem or a regression problem. So you have this data A and B, A is a matrix, and you're trying to solve AX equals B. And you can do this with an optimization algorithm by minimizing the 2 norm of AX minus B. And so how do you make an average case complexity result out of this? Well, you now assume that your data is random. So that means that this A and B from your regression is actually random, okay? And then we can run optimization algorithms off of it. And we usually measure the complexity for an optimization algorithm as sort of the number of iterations until the gradient is small. The gradient being small means that we minimize the problem, okay? And here, what I'm showing you is gradient descent. So gradient descent is a classic optimization algorithm where you just move in the direction of negative the gradient. That's how you iterate the algorithm. And what you see here is something really cool, which is that as you make n large, so as you make the dimension of your matrix larger and larger and larger, you can see that the number of iterations or the complexity is all converging to the same value. And amazingly, what is even more surprising is that it doesn't actually even depend on how you chose this random A and B. You could have chosen it from Bernoulli, you could have chosen it from Gaussian, it doesn't matter. They all go to the same type of complexity result. And this turns out to be true of all first order algorithms. So all high dimensional first order algorithms in general have this property, which is that they're kind of robust to the data that's coming into it. So it's kind of a cool result. And what you can do is you can actually characterize what this gradient looks like based upon the algorithm, which is really a neat thing that we were looking at. You can actually see precisely how the algorithm and the model and the noise and signal all sort of interact with each other. And you can characterize how it's going to exactly affect the convergence complexity. So that's what we did in this work here. And you can see this in this picture of how so the algorithm and the data model all interact. And this idea goes beyond just regression, which is also a really nice phenomenon. It works for other types of objective functions, which we typically use in, say, machine learning or artificial intelligence. So for instance, logistic regression. It also works for different algorithms, like stochastic algorithms. So a typical stochastic algorithm in, say, machine learning is stochastic gradient descent. We see the same phenomenon, that somehow as you make data get larger and larger and larger, your optimization problem actually gets easier, which is sort of counterintuitive, but very interesting. And then you can compute average case complexity results. And you can see for lots of different algorithms, so this is the gradient descent one, that you actually get better complexity than the worst case one, and by orders of magnitude. So it's pretty significant by doing this average case that a typical user on these algorithms are going to have better performance than what we would have expected from the worst case. And I just wanted to finish by saying that this idea, there's a lot of cool things that we can do with it, and I'm hoping that to continue this research at McGill and get a lot of people involved. There's how do we do these types of results for stochastic algorithms? Can we do these things with neural network structures, which are more typical for machine learning? Can we use different matrix ensembles? How do we do this randomness, non-convex functions? And then finally, I think which would be really cool is how do we actually design new algorithms based on average case complexity instead of basing it on worst case complexity. So I'm hoping students might be interested in this. And if you have questions, I would love to talk to you guys about it. So thank you very much.
And thank you, Courtney, and welcome to McGill. It's fantastic to have you finally get here, and I know under quite difficult conditions to get here. It's great to see you and great to hear about your work. Our next speaker is a feature of Soup and Science. We have an undergraduate research student, someone who's benefited from the experiences that we hope that all of you will be able to have in the course of your degree. And I'll turn it over to you, Mr. Taj Dyson.
Hello, I'm Taj. I'm a third-year physics undergrad, and I've worked on radio frequency interference at the McGill Arctic Research Station with Professor Cynthia Chang, who I actually met at Soup and Science in 2018, and Jonathan Sievers. What they're interested in, if you look at the diagram in every cosmology talk, they're interested in imaging the universe in the dark ages. Now, the dark ages are just before the first stars formed, but after the cosmic microwave background, and they're one of the least studied eras of the universe's history. One of the reasons for this is that the only signal that comes from the dark ages comes from neutral hydrogen, which faintly glows at around 1.4 gigahertz. But by the time that signal reaches us on Earth, it's been redshifted down to 100 megahertz, which is pretty much exactly the frequency of FM radio broadcasts. So that radio frequency interference, or RFI, gets in the way of the natural signal we want to see, and that poses a huge problem. And one of the simplest and therefore best ways to mitigate this problem is to just geographically distance yourself as much as possible from the source of this RFI. And that's what Professor Cynthia Chang, Dr. Raul Monsalve, and I did last summer, the summer of 2019, is we went up to the McGill Arctic Research Station, or MARS, and we set up our antenna there. And we took some preliminary measurements. Now, of course, the world is not ideal, so even though we're very far from any population centers, RFI still gets in from satellites and military communications and all sorts of things. So my job this summer was to look at the data and determine exactly how much RFI still got into our data and at what frequencies. And that would help answer, is the McGill Arctic Research Station a good place for our measurements? So how do I do this? Here's what the antenna gives me. Here we have the radio intensity, the kind of intensity of the radio waves in color. So yellow is more intense as a function of frequency along the horizontal. So these are all of our frequency channels, like you're tuning your radio, and time along the vertical, falling downwards like a waterfall. It's called a waterfall plot. So here you can see I've got one night of data for an example. We've got about a month worth of data to look at, but this is just an example. What are we looking for here? We're looking for human-generated RFI. And the way we know what that is it's typically very narrow in frequency and very bright compared to the natural signal. So I want to get rid of all wide signals so that I only see the very narrow RFI signal that I want to look at. And I tell my computer to do that, and I zoom in the color scale so I can see fainter things. And now we see only the very narrow features, which are all human-generated RFI, which I want to classify. And I go from this continuous data, which is this number is bigger than that number, and I turn it into a yes or no question. Is this data RFI or is it not? Is it clean? And we see that it looks like there's a lot of white marked as RFI, but it's actually very clear compared to many other radio sites. We see from around 90 to 100 megahertz, which is the FM band, is usually completely swamped with RFI, but here it's actually very clear. Below 20 megahertz, there's a lot of RFI, and that's not great, but in general, very good. We also did a survey around various locations near the McGill Arctic Research Station to see if the mountains and ridges and fjord affected the RFI distribution at all, and it didn't. So it's great everywhere. That's nice. On the right, you can see there's our helicopter pilot compared to the scale of a glacier. I think that's a very strong image. And in the future, we want to take measurements over the winter. We were going to go to the McGill Arctic Research Station to do that this summer, but unfortunately that didn't happen for circumstances outside of our control. So next summer, we want to set up our antenna, take measurements over the winter when we hope the RFI will be better because there will be less human activity and less ionosphere activity. So I'm looking forward to seeing that data. And I'd like to thank NSERC, and I'd like to thank NSERC for funding, of course, and I'd like to thank you for listening to my talk.
Thank you, Taj. Fantastic. Very, very inspiring, your work, and a great example of how you're working on a world-class problem with world-class researchers, and you're an important part of that team. As a side note, to those of you who might not be interested in setting up antennas in the top of the world, but this McGill has the most northerly research station, permanent research station of any university in the world. That's at 80 degrees north, Axel Heiberg, where that we just saw those images. And so our members of this Earth and Planetary Sciences, members of Faculty of Agriculture and Environmental Sciences, each year have research programs in the very, very short summer that is featured at 80 degrees north. But so there's a lot to do there, plus or minus the interesting wildlife that you have to share the island with. So thank you. 3 great presentations, and now our 4th presenter, Professor Vicky Kaspi, and she's going to tell you about her work with her colleagues in the Department of Physics and the McGill Space Institute. Over to you, Vicky.
Okay, thanks, Dean Lennox, and it's a pleasure to be here. I'm going to be sharing my screen for this presentation because it was simpler to do it that way. I hope, can everybody see my screen?
Yeah, it's coming in fine.
Okay, great. So I'm really happy to be here, and I'm going to tell you about fast radio bursts. Basically, when people ask me, what am I working on? I say, I don't know, because these are mystery objects, something that's a new astrophysical puzzle. We don't know the origin, as I'll explain. So here's a little cartoon just to sort of, get across what, the idea here. These are brief bursts of radio waves. They last only a few milliseconds, and they're all over the sky. They're coming in pretty often, as I'll explain, and we know that they're coming from far, far outside our own galaxy, from the sort of cosmological distances that you just heard Taj talk about. There's only about 100 of these published since their discovery in 2007. And yet we can infer that the rate of these on the sky, if you could look everywhere all the time, 24 hours, you would see about 1,000 of these events happening. So this is something incredibly common in the universe. This isn't an anomaly. This has been happening, since the dawn of time. We've only just realized it. But their origin is totally unknown. We don't know what's causing them. The fact that they're so far away at cosmological distances tells you they must be extremely powerful explosions, but we don't know their nature. So they're random in direction. We don't know where or when they're going to come in. You might wonder, how is it possible to study a phenomenon like that? You need a telescope that can look everywhere all the time. Now, this is sort of a media version of how we do radio astronomy. You have a radio dish and something magical happens exactly where it's pointed. Now, first of all, radio waves are invisible, so this is silly. But second of all, if you have a transient phenomenon, it's really hard to use a conventional radio telescope because it can only look in a very limited area of sky, and the chances of you seeing one of these fast radio bursts is really small. So this is not how we see fast radio bursts. In fact, this is how we actually see fast radio bursts. And I thank Taj for showing you already a waterfall plot. This one's rotated by 90 degrees. So radio frequency is on the y-axis and time is on the x-axis. And this is not months like Taj showed you. This is milliseconds. So you can see, first of all, an annoying television station. There's some RFI right there at a fixed frequency that's on all the time. The signal that we're interested in is the one that you see sweeping in, and that sweep is a form of dispersion due to the interaction of radio waves with plasma in the intervening interstellar and intergalactic medium. When we digitize all of our data in both time and frequency as Taj does, and then we correct this sweep in software, and the inset is the burst. You can see there's nothing beforehand, just static of the radio telescope. The sudden burst that's there for a few milliseconds, and then it disappears and we don't see it again. So that's what the phenomenon is. Now, how do you study this kind of phenomenon? Well, we've built a new radio telescope here in Canada, the CHIME telescope. It stands for Canadian Hydrogen Intensity Mapping Experiment. And if you look at that thing, you might think that doesn't look like a radio telescope, and yet it is. It's a revolutionary design that includes 4 cylinders, like half pipes, that are about 20 meters by 100 meters long. So the total collecting area here in Canadian units is 5 hockey arenas. You can see our team standing in the axis of one of these cylinders to give you some scale. There's no moving parts. You can't point this telescope. It can only see what is directly overhead. It's oriented north-south, so the sky, as the Earth rotates, the sky rotates, and the telescope sees what happens to be overhead. Each cylinder, has 256 antennas on its axis. So it's a total of 1,024 antennas, each with 2 polarizations. So we have 2,048 input signals that are being digitized very rapidly. Our input data rate is 13 terabits per second, which is comparable to the world's cellular network. So there's a massive amounts of digital processing going on at the site in shipping containers that are seen off to the side here, which might be behind Bruce's head, actually. At least it is in my version of Zoom. So I don't know what you're seeing, but anyway, there's 2 little shipping containers there. Now, why would you build that kind of telescope? A conventional parabolic dish looks at one position on the sky, and a transient phenomenon, as I said, you're going to miss all of your events. But in a cylinder focuses only in one dimension. You see a huge swath of sky, and in our case, oriented north-south. And so this kind of geometry for a telescope lets you have an enormous field of view. And comparing that to a conventional radio telescope, it's hundreds to 1,000 times larger. And so your probability of detecting a transient event is that much larger as well. In fact, my Earth is supposed to start rotating. There we go. Here it goes. You can see the bursts going off, and you just catch way more of them this way. I'm going to skip this slide because I don't have time. But basically, the point is it's massive amounts of computing going on right alongside. We have a supercomputer there. And this whole thing is built by students and postdocs. This is very few. We have a few professional staff on hand, but it's really students like you, including undergraduates, who have helped with our cabling, with our programming, with our data analysis. So far, we found over 1,000 fast radio bursts, and we're working on the world's first major fast radio burst catalog that lets us look at all sorts of different distributions of properties of these events. Incredibly illuminating. Stay tuned. We have found 18 repeating fast radio bursts. Some of these sources don't go away forever. Some of them come back, and that is a fascinating thing to study. One of them we found repeats regularly every 16 days, and we don't know why. Okay, I don't know why. We've even found probably one galactic fast radio burst, something in our backyard. That's a paper coming out in Nature very shortly. And I'll just end by saying, stay tuned, lots more results. There's the team, and thank you very much to all of our funders.